Welcome to part 2 of my videos on connecting a 7-segment display to a Raspberry Pi using the I2C interface and a MCP23008 integrated chip. We're now ready to connect our chip up to the Pi and detect it on the I2C interface, for which we need to understand the connections that the chip provides. When you look at the MCP23008, you will find that one end of the chip has a small notch in it. This identifies the end where pin 1 is, so that you can match your chip up to the diagram. The SCL pin is the serial clock input, and the SDA pin is the serial data line. These comprise the dual wire interface that is I2C. Pins numbered 3, 4 and 5 on the chip provide addressing, which we will cover in the future video, but in short enables the I2C interface to address multiple chips separately. Pin 6 enables a reset feature, and pins 7 and 8 will not be covered in this particular application. The VSS and VDD stand for voltage source and voltage drain. Don't be fooled by the conventional current analogy, however, as these symbols follow electron flow, which means VSS connects to ground and VDD connects to the 3.3 volt or 5 volt pin on the Pi, also known as the positive terminal. That leaves us with pins 10 through to 17, which are the 8 configurable bits of the input-output expander. The I2C interface will send and receive byte commands from the Pi, and based on the command received, be able to turn these pins on and off. Firstly, we need to get some connections happening between our Pi and the MCP23008. I'm going to create this circuit using a breadboard to test that our I2C interface is operable and that we can send commands to the chip. For the setup, I'm going to use pin 1 on the Pi, which provides 3.3 volts DC and is connected to the vertical power rail on the breadboard. Pin number 6 on the Pi is a ground connection, and this is connected via the black cable in the diagram to the vertical ground rail on the breadboard. For tidiness, you will see that I have linked the two vertical rails on the opposite side to the same on the left. This provides easier connectivity from the right-hand side of the chip's pins as required. Note here that the chip has its notch, which identifies pin 1, at the top. The next step is to connect the I2C interface, which we will do by connecting pin number 3 on the Pi to pin number 2 on the chip. This is the yellow wire in the diagram. Pin number 5 on the Pi to pin number 1 on the chip, which is the blue wire, provides the serial clock input. We then need to set an address for the chip, which I will do by connecting A2, A1 and A0 all to the ground pins, which are pins 3, 4 and 5 on the chip. This will provide the chip with its default address of the hexadecimal value 20. To ensure that the chip always starts in a default state, I'm going to connect the reset pin, or pin 6, to the power rail. Lastly, we need to connect our chip to the circuit we have created by linking pin 9, VSS, to the ground rail, and pin 18, VDD, to the 3.3 volt power rail. Here's another quick check to make sure that we have our chip pins all connected to the correct components. Before we test our Pi, we'll add something easy to test it with so that we can see some visible evidence that we have managed to send a command via I2C to our chip. For this, I'm going to use the humble 3mm red LED connected to GP0 on the chip, or pin 10. I'm going to do this by connecting the longer leg, the positive one of the LED, to the same row as pin 10. To ensure nothing will be damaged on the Pi, I'm also adding a 270 ohm resistor to limit the current from the Pi on the negative leg of the LED. This will be attached to the ground rail. Our circuit is connected and ready to go. It's time to power on the Pi and see if our chip is detected. There are several commands which we are going to run to test out our circuit, but before we do so, we need to ensure that our chip has been detected. Run the I2C detect command again, this time with the expectation that our MCP23008 will appear in the output with a valid chip address. If you have wired this the same as mine, this should be something like 0x20, or the hexadecimal value 20. Next, we are going to tell the chip that we need some output pins. By default, all configurable pins are set as input, so we do this by accessing the input-output direction register, which is at address hexadecimal value 0. The commands are all using hexadecimal byte addressing, so we'll need to understand a bit of binary and convert this to hexadecimal. If you're already familiar with hexadecimal notation, then you should have figured out that 0xFE is the command needed to enable our test pin. Here's how to figure that out. The top pins on the MCP23008 when viewed in this orientation are numbered 0 through 7, from right to left. Each of these will either be on or off. When the chip is powered and reset, all pins are set to on, which makes them input. To change a pin to an output, it needs to be set to off. This is performed through the binary 1 for on or 0 for off. If we display the default state for the direction register, all 8 pins will have a 1, which means they are set on for input. Each 1 or 0 is referred to as a bit. There are 8 bits to a byte, but we will group these 8 bits into 2 sets of 4 bits, each made up of 1s. To complete the conversion into hexadecimal are the appropriate single-digit character that represents this 4-bit code. As each bit can be a 0 or a 1, there are only 16 permutations that exist, from 0000 through to 1111. Here's a quick view of the hexadecimal reference for the binary pins. As you can see from this, the value for 1111 gives the hexadecimal value of F. Our last pin, GP0, is the one we want to change. So in the second 4-bit address, we need the equivalent of 1110, which you will see here is E. That means that when combined, our 8-bit address is 11111110, which becomes the hexadecimal representation FE. Let's set this pin to an output by running the command I2C set, to do which we need to address the device bus, then the chip address, then the input-output direction register, and then provide the byte command that we require. The command I2C set first takes the -y parameter, which suppresses the prompt asking us, are we sure we want to do this? The next parameter is the device bus, which for the Raspberry Pi 2 is 1, and for older versions 0. The next parameter is the chip address, which we retrieved from our I2C detect command. For me, this is 20. The 0x tells the chip that this is hexadecimal notation, so it knows that we are sending this byte command and it can understand it. The next parameter is the chip register, which for this example we want to instruct the I/O direction register. This can be found in the MCP23008 specification sheet and is found to be 0x00. Lastly, we need to send that code we've just worked out to be 0xFE, telling the chip that pin number 10, or GP0, needs to be changed from an input to an output. Once the direction register has been changed, We are now able to perform our much anticipated test with our humble red LED connected to GP0 or pin 9. We're going to run the I2C set command again, this time addressing the GPIO port register on the chip. This can be found in the specification to be the hexadecimal value 9. As by default, an output pin state is off. To set it to on or high, we need to turn that bit on. We do this by determining that all our input pins will be set to 0 and that our output pin will be set to 1. This gives us the 8-bit address of 00000001. When converted to hexadecimal, that is of course 01. Sending the command I2C set -y 1 0x20 0x09 0x01 should show us the LED turning on. To turn this off again, we simply run the I2C set command, changing the command from 0x01 to 0x00. The last thing I'll show you here is how to use a Python script to send the commands we need to flash our LED on and off a few times using I2C. On your Pi, you can open up idle by typing idle from your terminal window. This will load the application which will happily run any Python commands you send it. Alternatively, you can write your script and save it as a .py using Nano or some other editor. This is a basic script I've created that does the following. At the top we import the SM bus and the time modules. We then assign various values to some variables so that we can refer to them throughout the script. You'll see here that I have used my address of 0x20 for the chip, and I have the input-output direction register and the GPIO registers already pre-configured. First thing I've done is write byte data with the 0xFE to make sure that that pin is set as an output. We then have a for loop that turns pin 9 on for half a second and then turn it off again and waits half a second. That will repeat. Thank you for watching. In part 3 I'm going to extrapolate on what we've done here by connecting an LED 7-segment display to the MCP23008. We can then control this using the GPIO register commands on the microchip via I2C.